So welcome students. Today we are going to deal with the topic of sets. As you know, this topic of sets is the very first topic of your class 11th syllabus. And this is a very easy topic also. So before going into the topic of sets, let us first have a rough idea of what we are going to learn in this topic. So this topic's code word is dream, talkies, come, fall in love. This is the code sentence for this topic. So let us see what this means. So to understand this, so the topic of sets is basically divided into two parts. The first is the theoretical part. The other is problems part. So in the theoretical part, we learn basically three different topics. The first topic is definitions, that is what sets are and the basic definition of different terms that are there in sets. And the second is representation of sets, that is how do you represent sets, how do you write sets. And the third is terminology. So we study the basic terms, the new terms that you get in this chapter. So these three constitute the theoretical part, that is the basic study that you need to do before going to the problem section. And once you are conversant with these three topics, next you go to the topics where problems will be asked. So those topics come under four headings. The first is the topic of Venn diagrams. The second is operations, the operations that we do on sets. And the third is laws of sets. And the final topic is formulae. So what are the different formulae that we have in sets? So these are the 7 topics that you're going to learn in the topic of sets. And do you see what dream, talkies, come, fall in love is? That is nothing but DRT denotes. DR and T denotes definitions, representations and terminology. And come, fall in love denotes formulas, laws, operations and Venn diagrams. So whenever you remember the topic of sets, just remember this sentence, dream, talkies, come, fall in love. So this sentence gives you the order of different topics that you need to remember in this chapter. Now let us go into each of these individual topics and study them in detail. So now let us go to the D part of our code sentence, that is the definition part. So what is the definition of a set? A set is a collection of well-defined and well-distinguished objects. So a set is a collection of well-defined and well-distinguished objects. There are two words in this definition. So obviously you can see that we are talking about a collection of objects, right? You know what a collection means. Collection is a group of objects. So let us say I'm talking about collection of vowels in English alphabet. So I'm talking about a collection of vowels in English alphabet. So is this set well defined? So obviously we're talking about some collections. You know that in the collection of vowels in English language you have 5 letters A, E, I, O and U. So is this collection well defined? So well definedness means that when you define a set, the definition of this set has to be very clear. That means if you take any object, you should be able to tell whether that object belongs to this set or does not belong to this set. So once you have defined the set, this is the definition of this set. That is, this set contains vowels of English language. That's how I describe a set. Now, once I describe this, so is this well defined? Yes, because if I take an object B, so you have a lot of English alphabets, A, B, C, D, E, F, G, H, so on, up to Z. You have 26 English alphabets. Now, once I have given this description for this set, you should be very clear whether if you take an object A, so does A belong to this collection or not? The answer is yes, because A is a vowel. Does B belong to this set? No. Does C belong to this set? The answer is no. Does D belong to this set? The answer is no. Does E belong to this set? Yes. So the answer has to be either yes or no. There should not be any ambiguity. So such collections are called well-defined collections. So AEIOU or collection of vowels in English language, English alphabet, is a well-defined collection. And the collection has to be well distinguished also. Well distinguished means that each object should be distinguishable from the next object. So if you take any two objects in this set, they have to be distinguishable. They should not be exactly same. That means if I say the collection of vowels in English alphabet, you cannot write A, E, I, O, U. This is not the collection that I am talking about. Because if I write A 2 times, these two elements are not well distinguished. So well distinguishedness means that an element comes in the set only once. It does not come twice. So I say that in the collection of vowels in English language, how many elements are there? There are 5 elements, or there are 5 objects. So if this property is not there, if well distinguishedness property is not there, I would have as well written like this. That means this set might have more than 5 elements. So to cut down this ambiguity, so in the definition it's given that a set is a collection of well-defined and well-distinguished objects. So usually we enclose a set in flower brackets. We enclose the objects of this set in flower brackets. So let us take an example where this well-distinguishedness is not getting satisfied. So if I say I want the collection of good teachers. So if I want the collection of good teachers, this is not a well-defined property, because good is not a well-defined property. Because some teachers you might feel good and the others might not feel good. So good is a subjective. Good is subjective. It's not an objective word. So whether a teacher is good or not depends on my subjective opinion. So such collections cannot be considered as mathematical sets. So once you say that a collection is a set, it has to be well defined and well distinguished. So next, the objects in the set are called elements. The objects present in the set are usually called elements of set. So how many elements does this set have? This set has 5 elements. This set has 5 elements. And sets are usually denoted by capital letters. Sets are usually denoted by capital letters. And the objects of this set are enclosed in flower brackets, and you use a comma for each object. So you can as well call this elements, right? So sets are represented by capital letters, and objects of this set are usually called elements, and elements are enclosed in flower brackets. And we say that every element of the set A belongs to A. That is, I write the element A belongs. This is a new symbol for you. It stands for belongs to. So the element A belongs to the set capital A. And the element B belongs to, does element B belongs to set A? No, element B does not belong to set A. If you write belong to and put a, if you cross it, then it means does not belong to. Does not belong to. So A is an element in A, so I say that A belongs to A, and B is not an element of A, so B does not belong to A. So each element of the set belongs to that set. So now let us go to our second topic, which is representation of sets. So how are sets represented? How are sets written? So sets are represented in two forms. The first is roster form or list form or tabular form, so on. So all these are the different ways of saying the same thing. So roster form, list form or tabular form. And the second is set builder form. So sets are usually represented in two ways, roster form and set builder form. So let us see what these forms are. So before going to that, so let us look at some of the sets that you know in your lower classes, some of the number sets. So you already know some sample sets, which are the set of natural numbers. So you know what a set of natural numbers is. Set of natural numbers is the set containing 1, 2, 3, so on, all the counting numbers. And the set of whole numbers, I don't need to explain what set of whole numbers is, you know what they are. And the set of integers, the set of rational numbers, the set of irrational numbers, the set of real numbers, so on. So these are some of the standard sets that you know. Natural numbers goes from 1, 2, 3, so on up to infinity. Whole numbers start from 0, 1, 2, 3, so on up to infinity. Integers have both positive numbers as well as negative numbers. Q, rational numbers are nothing but quotient numbers. That is, the numbers written in the form of P by Q. Irrational numbers are the numbers which are not rational. Real numbers are a total set containing both rational and irrational numbers. Now, how can we represent these natural numbers? So you know what natural numbers are. So how can you write the set of natural numbers? So the set of natural numbers can be written as, in a flower bracket, 1, 2, 3, 4, 5, so on. So in this representation, we have enclosed the objects of this set in a flower bracket. That is what we usually do for sets. And each of these elements are listed. That is 1, 2, 3, 4, 5. All the numbers are listed one after the other. So this type of representation is called roster form. That is, you list all the numbers. That's why it's also called list form or tabular form. You tabulate all the numbers. A roster, if you look at the word in your dictionary, this also represents a log book where all the names are written. So the whole numbers, the set of whole numbers is nothing but 0, 1, 2, 3, 4, so on. This is also a roster form of representation. That is, you list all the numbers, all the elements of the set. So what is the set of integers? The set of integers are so on, so on, so on. -3, -2, -1, 0, 1, 2, 3, again so on. This is a set of integers in roster form. And we don't write the set builder forms for this because they are so basic that you need to understand what they are. So using these sets, we write the set builder form for complicated sets. Now, so let us talk about this set. So let us say that we have a set A. We have a set A which contains the numbers 1, 1 by 2, 1 by 3, 1 by 4, so on. So let us say that a set A is 1, 1 by 2, 1 by 3, 1 by 4, so on. So obviously this is a set. So you know what this set is containing. So this set contains numbers of the form 1 by 1 by 2, 1 by 3, 1 by 4, 1 by some natural numbers, right? So this is the roster form of representation of the set. Now this set can be represented in other way. So this set can be represented like this. This set contains numbers of the form 1 by n. This set contains numbers of the form 1 by n such that n belongs to natural numbers. So when I write this and when you read this as I have read, do you understand that this represents the same set as this? So I read this as set containing the elements of the form 1 by n, where n is some natural number. That is, n is 1, so you get 1 by 1, n is 2, 1 by 2, n is 3, 1 by 3, n is 4, 1 by 4, so on. So this type of representation is called set builder form. So in set builder form, we try to catch the property of this set, the property of the elements of this set, and will exhibit that property so that I can build the set myself. For example, so if I write the set containing the elements of the form n by n plus 1 such that this line represents such that n belongs to natural numbers. So if I tell you this, can you intelligently construct this set? Yes. So if I have to construct this set becomes B is equal to the set containing, if I have to write it in roster form. First, n is a natural number, so n becomes 1 first. 1 by 1 plus 1 is 1 by 2. Next n becomes 2. 2 by 2 plus 1 is 2 by 3. 3 by 3 plus 1 is 3 by 4. 4 by 4 plus 1 is 4 by 5, so on. So this is the set I am talking about by this set builder form. So if you write the elements sequentially, one after the other, if you list all the elements, that type of representation is called roster form. So if you exhibit the property of the elements of this set, then such representation is called set builder form. So the form of set builder form is nothing but, so in the flower bracket, the element x such that x has a certain property. So this is how the set builder form of a set looks like. So let us look at some more examples to better understand roster form and set builder form. So let us look at these examples. So in the first example, A is a set of odd positive integers less than 100. So how do we write this in, how do you represent this in roster form and set builder form? So this is a description which is given in English. So let us write the mathematical way in which this can be written. So the roster form is, you can see this A is a set of odd positive integers less than 10. That means you have odd positive integers start from 1 and you have only odd numbers 1, 3, 5, 7 and 9. So these are the odd positive integers which are less than 10. So this will be the roster form for this. So what will be the set builder form for this? Set builder form is nothing but a set containing an element x such that can be represented by a vertical line or a colon also. Both represent the same thing. So x such that x is a positive integer and x is odd. I can write it like this. So A contains element x such that the property is listed in the next section. X is a positive odd number and x is odd. This is one way to write this. So there are better ways to write this set in set builder form also. So let us write it like this. A is a set containing elements of the form 2x plus 1 such that, so you know that odd numbers will look like this, 2x plus 1, where x belongs to z integers and what should be the value of x? X has to be in between, right? So x can start from 0. If x is 0, the element becomes 1. If x is 1, the element is 3. X is 2, the element is 7, element is 5, x is 3, the element is 7, x is 4, the element is 9. So I want only elements till 9. So 0 less than or x less than or equal to 4. So what does this mean? A contains elements of the form 2x plus 1, where x belongs to integers and x is in between 0 to 4. That means x cannot take all the integer values. It has to be starting from 0 and going till 4. That is 0, 1, 2, 3, 4. You can take 5 values. Correspond to 5 values of x. You get 5 values 1, 3, 5, 7 and 9. So this can be a set builder form. This can also be a set builder form. You can write whatever you want. Or you can think about other ways also. Set builder form is not unique. It's not like you have only one way in which you can write the set builder form. You can write in any way. Such that, but once you write, if I apply the properties, I should be able to get the exact set that I am talking about. So next, let us go to set B. Set B is the set containing letters of the word statistics. So this is a very tricky question. So what is the set builder form of this set? Set builder form of this set is nothing but, so what are the letters that are present in the word statistics? You have an S, you have a T, you have an A, so you have a T again. So you cannot write T again here, because once you write the roster form, the elements cannot be repeated, because the elements of a set have to be well defined and well distinguished. So I cannot write a second T, then these two T's will not be well distinguishable. So S, T, A, so this T has already been listed. So you have an I, and next you have an S which has already been listed, T is already listed, I is again already listed, C is not listed, and S is already listed. So the set of letters of the word statistics contains only 5 elements. That means the word statistics is formed only by 5 letters. Some letters are repeating. And what is the set builder form for this? B is nothing but the element, set containing an element x, such that x is a letter of word statistics. So I can write it like this. Or x such that x belongs to the set S, T, A, I, C. That can also be a set builder form. So you have to make sure that once you have a description, if you expand it, you should be able to get the set that we are talking about. So now if you have set C, x such that x is a positive integer and x is square less than 40. A set builder form is given. So what is a roster form for this? So this set C contains elements which are positive integers such that x square, when you square that number, it is less than 40. So positive integers start from 1. So that is 1 square less than 40, yes. 2 square is also less than 40, 3 square is less than 40, 4 square less than 40, 5 square less than 40, 6 square is less than 40. But 7 square, so if you take the element 7, 7 square is greater than 40, so 7 does not belong to this set. So you have only elements till 6. So if you take the set D, D contains 1, 4, 9, 16, 25, so on. This is a roster form. What is the set builder form for this? So clearly you can see that these are squares of natural numbers. So when you write set builder form, you have to catch that property. So this is a set of the squares of natural numbers. So how do you write this in set builder form? Set containing elements of the form n square such that n belongs to natural numbers. So n is a natural number, but the element of my set is n square. So when n is equal to 1, you have 1 square. N is equal to 2, you have 2 square. N is equal to 3, you have 3 square. N is equal to 4, 4 square. N is equal to 5, 5 square, so on. So this will be the set builder form for section D, set D. So I hope you understood how you can write roster form and set builder form. And what you need to remember in this topic is set builder form need not be unique. That means for the same set, you might write one answer, your friend might write one answer, both of you might be right. So set builder form is right as long as you can build the set from the given definition. So now let us go to the third topic of terminology. So let us look at some new words that we need to understand. So let us take the first set of words, that is null set, singleton set, finite set, infinite set, equal sets, equivalent sets. These are the 6 words that we are going to learn. So first, what is a null set? So a null set is a set containing no elements. Set containing no elements. That means a null set is an empty set or a void set. So null set does not contain any element. Example, if I write A is set of integers whose square is 2. So if I am talking about this set, I want the set of integers whose square is 2. So is there any integers whose square is 2? So you know that there is no integer whose square is 2, because if x square is equal to 2, x has to be equal to root 2. But root 2 is not an integer. There is no element in the integer set whose square is 2. So what is the set A if I have to write it in roster form? So what are the elements present in this A? There are no elements. So I write it like this. So A is a empty set or null set, and null set is usually represented by a square bracket containing no element. So this is a null set, and this is also denoted by the symbol phi. So phi means also null set. So a flower brackets containing no element or phi. So this is usually read as phi. So phi in set theory represents a null set. The set of integers whose square is 2, or the set of positive integers less than 1. Set of positive integers less than 1. So are there any positive integers less than 1? No. Hence B is also a null set, or B is phi. And what is singleton set? Singleton set is a set containing only one element. So singleton set is a set containing only one element. So if you have a set containing only one element, that is called a singleton set. So you have lots of examples for singleton set. So in a class, the set of students who got first rank. In a class, the set of students who got first rank. So first rank is obtained by only one student, hence you have a singleton set. So the set of positive integers less than or equal to 1. So you have a singleton set. That is set 1. So on. And finite set and infinite set are clear from the name itself. Finite set is a set where the number of elements is finite. You have countable number of elements, then it's called a finite set. Uncountable number of elements, you have a infinite set. And regarding finite set, you have another word called cardinal number. So the cardinal number of a set, for example, set A is denoted by n of A. N of A is nothing but number of elements in A. So the cardinal number of set A is nothing but number of elements in set A, and it is usually denoted by n of A. Cardinal number is also called order of A, order of set A. This is also same. So order of set A and cardinal number are both same. So it is denoted by n of A. So n of A is nothing but the number of elements in A. So for example, what is n of null set? Number of elements in null set is 0. So n of phi is nothing but 0. So what is n of a singleton set? For a singleton set, n of A is equal to 1. So on. So for a finite set, cardinal number represents the number of elements in that particular set. Next, you have two more terms, equal sets and equivalent sets. Equal sets A and B are equal if they contain exactly the same elements. Two sets A and B are equal if they contain exactly the same elements. Each and every element have to be same in both sets, then they are called equal sets. And what is equivalency? Equivalent sets are nothing but the sets containing same cardinal number, or the sets containing the same number of elements. If the number of elements in two sets is same, then they are called equivalent sets. If the elements are exactly same, then they are called equal sets. Obviously, equal sets automatically become equivalent sets, but equivalent sets need not be equal sets. I hope things are clear. So these are the first 6 terms that you need to know. Null set, singleton set. Finite sets, infinite sets. Equal sets, equivalent sets. It's always better to remember things in pair. So when you remember things in pair, both of them will be nicely remembered. So instead of remembering one by one, you remember in pairs. Null set, singleton set. Finite sets, infinite sets. Equal sets, equivalent sets. Now let us go to the next set of terms. So now let's go to the next set of terms. Subset, superset, proper subset, power set, comparable sets, in universal set. Again, you have 6 terms. So let us see each of them. So subset. So let us see an example. So if you have a set A, which is a set containing 1, 2 and 3. And let us take a set B, which is a set containing 1, 2, 3, 4, 5. So you can see that every element of set A is also present in B. So 1 is present in A, is also present in B. Similarly, 2 is also present in B. 3 is also present in B. So if every element of A is also an element of B, then we say that A is a subset of B. This is the symbol for subset of. A is a subset of B. If every element of A is also present in B. Is it clear? Subset. Next, you have something called superset. Superset is exact opposite for subset. If A is a subset of B, then B is a superset of A. So you can relate this with less than or equal to and greater than or equal to in numbers. So A is a subset of B. That is, every element of A has to be present in B. So why do we have this equal to symbol? Because if you have a set A as 1, 2, 3, 4, 5 instead of this set. If set A is 1, 2, 3, 4, 5 and set B is also 1, 2, 3, 4, 5. Now also, every element of set A is also an element of B. The definition is being satisfied. So I have to write A is a subset of B also. That is, every set is a subset of itself. So every set is a subset of itself and every set is a superset of itself, because the definition is being satisfied. That's why we write something like less than or equal to. This is not a sharp less than, this is a smooth and less than. So A is a subset of B, B is a subset of A. So I hope these two are clear. You have to remember the definition. A is a subset of B, A is a subset of B if every element of A is also present in B. And superset is the exact opposite for subset. Next you have something called proper subset. So proper subset. So this is denoted by A is a proper subset of B without is equal to. So A is a proper subset of B if A is a subset of B and A is not equal to B. So B should contain at least one element which is not present in A. Then it is called a proper subset. So I hope this is clear. So 1, 2, 3 is a proper subset of 1, 2, 3, 4, 5. But 1, 2, 3, 4, 5 is not a proper subset of 1, 2, 3, 4, 5. So A is not a proper subset of itself. A is a subset of itself, but A is not a proper subset of itself. Next, power set. This is important. So if you have a set A, 1, 2. So what are the subsets of A? What are the subsets? Obviously, empty set is a subset of every set because empty set does not contain any element. So whatever are the elements in this set, they are also present in A because emptiness is also present in A. So empty set is a subset of every set. So that is one of the property for subset. Every set is a subset of itself and empty set is a subset of every set. So one of the subset is 5. Next you have a subset containing a single element 1, a subset containing a single element 2, and a subset containing 2 elements, which is itself. So if you take a set 1, 2, there are 4 subsets. So what is a power set? Power set of A, P of A, is nothing but a set containing all the subsets of the set A. Empty set, set 1, set 2, set 1, 2. So this is called the power set of A. So I hope this is clear. Power set of A is a set containing all the subsets of A. The power set of B is a set containing all the subsets of B. Power set of C is a set containing all the subsets of C. So to write a power set, you first have to write the subsets, and once you write the subsets, you can get the power set by enclosing all the subsets in a set. So next, you have comparable sets. What are comparable sets? Two sets A and B are comparable if either A is a subset of B or B is a subset of A. If one of these conditions is valid, then they are called comparable sets. Either A has to be a subset of B or B has to be a subset of A. If nothing happens, then they are not comparable. And you have universal set. So universal set is a set containing all the sets under consideration. So if you have a problem in which you are talking about some sets, a superset for all the sets given in the problem is called a universal set. It is denoted by U. So before going forward, we need to understand the last term, which is open and closed intervals. So open and closed intervals. So what is the meaning of these intervals? So in many questions which come afterwards, you'll be asked to solve equations and inequations. So many a time you will be getting solutions something like this. X such that X belongs to real numbers and X is in between A and B. So assume that you have a set A which is denoted by this. This is a set builder form of set A. X such that X is a real number and X is in between A and B. That is, if you take a real line, so on the real line if you have two numbers A and B, you know what real number line is, and on that real number line you have two numbers A and B. So I want to denote all the numbers in between A and B. I want to denote all the numbers in between A and B, including A and B. A is a set containing all the numbers in between A and B, including A and B. So this set cannot be written in roster form because real numbers are continuous. You cannot write one number after the other number as you write in roster form. So there is only one way you can write it in set builder form. but you get this very often while solving questions. So we need a shortcut to write this. So x such that x belongs to R and x is greater than or equal to A and less than or equal to B. This interval is denoted by closed interval A comma B. So this square bracket denotes closed interval. That means A and B are included and all the numbers in between A and B are also included. So whenever you have, for example, closed 2 comma 3, this represents the set containing all the numbers between 2 and 3, including 2 and 3. So I hope you understood what closed interval is. This is just a notation. There's nothing much in this. From now on, you have to understand this as the set containing all real numbers between 2 and 3, including 2 and 3. Similarly, if you have a set like this, x such that x is a real number and x is in between A and B, but it does not include A and B. If it does not include A and B, that is, if you draw a real number line, you have A, you have B. So assume that you're talking about all the numbers in between A and B, but you're not talking about A and B. So let us denote this by a hollow dot. That means around A, let us take a hollow dot. That is, so now this means that you're talking about all the numbers in between A and B, but you're not including A and B. So this set is represented by open A comma B. For example, if this is 2 and if this is 3, you're talking about all the numbers in between 2 and 3, but not including 2 and 3. So you denote it by open 2 comma 3. So in coordinate geometry, this represents a point. But in set theory, in the theory of intervals, this denotes all real numbers between 2 and 3, but not including 2 and 3. Right? So this can also be represented by this. A square bracket which opens outward is also notation for open interval. So open interval can be denoted by either this or this. So whenever these two notations come, you need to understand that you're talking about all the numbers, all the real numbers in between these two numbers, but not including these two numbers. So once you understand open interval and closed interval, you can think about semi-open and semi-closed interval also. For example, if you have close 2 and open 3, what is the meaning of this? The meaning of this is that you're talking about numbers in between 2 and 3, including 2 but not excluding 3. So wherever you have an open bracket, that means that number is excluded. So you can also denote it like this: close to open 3. Instead of closing small bracket, you can have an opposite directed square bracket. So this also denotes close to open 3. These two are exactly same. So what does this mean? This means that you have an open 2 and close 3. It is between 2 and 3, 3 is included but 2 is not included. So depending on the placement of bracket, you need to understand which terms are included, which terms are excluded. So if you have both oppositely directed square brackets, that means open interval. So in inward directed square brackets, closed interval A comma B. So I hope you understood what the meaning of closed interval and open interval is. So now let us see some of the types of problems that might be asked in these topics, in the first 3 topics: DRT, definition, representation and terminology topics. So I hope you have understood the first 3 topics: definition, representation and terminology topics. So in these 3 topics, not many problems will be asked in the exams, but if you are to look at the types of problems that might be asked from your very basic understanding, so the problem types might be based on your understanding of a roster and set builder form. So might be asked questions based on this understanding. So next, you'll be asked questions based on the difference between the symbols belongs to and subset of. So there are two symbols that you have learned. In the definition topic, you have learned the symbol belongs to. Every element of a set belongs to the set. And in the representation topic, or in the terminology topic, you have learned about the topic subset. So you'll be asked to see the difference between belongs to and subset of. And third type of question is the question on number of subsets. You might be asked questions based on the number of subsets. So we have not done this in the terminology part because you'd have forgotten that. So number of subsets, you have to remember this very carefully. So number of subsets of a set depends on the number of elements of the set. So if n of A is equal to P, that means if there are P number of elements in the set A, then the number of subsets will be equal to 2 power P. So if a set has P a number of elements, then the number of subsets is 2 power P. So this is the only formula that you have in the first part of the set theory. So number of subsets is 2 power P. And finally, you might be asked questions based on open and closed intervals. So these are the 4 problem types that we are going to discuss in the first topic. All of these are very basic questions. So welcome students. So let us look at the problems based on the set builder form and roster form and in their interconversion. So first, let us say that you are given that A is a set containing an element x such that x square plus x minus 2 is equal to 0 and x belongs to R. What is the roster form of this set? So this set contains the element x such that this equation is valid. That is, if this x satisfies this equation, then it belongs to A, otherwise it does not belong to A. Now, what are the elements that belong to A? How do I get it? That can be obtained by just solving this equation. So you know how to solve the quadratic equation. X square plus x minus 2 is equal to 0. So if you factorize this, you get x plus 2 into x minus 1 is equal to 0. X plus 2 into x minus 1 is equal to 0. This implies x is equal to minus 2r plus 1. That means if this x square plus x minus 2 has to be equal to 0, x has to be either equal to minus 2 or 1. So these are the two elements which satisfy this equation. Hence these are the two elements which belong to set A. This implies set A in roster form is nothing but minus 2 comma 1. So this set contains two elements. So I can write n of A is equal to 2. If you're asked to find the number of elements in A, that will be equal to 2. So next, let us go to this question. So what does this set mean? B contains elements of the form x cube such that x is an integer and x square is less than 4, less than or equal to 4. So you know what integers are. So what are the integers such that their square is less than or equal to 4? So if their square has to be less than or equal to 4, x can be either minus 2, minus 1, 0, 1 or 2, right? So if you have the integers which are other than this, their square will be greater than 4. So minus 2 square is 4, minus 1 square is 1, 0 square is 0, all those are less than 4. Now, if x square is less than or equal to 4, then x has to be any one of these 5 integers. But my set B does not contain x. My set B contains elements of the form x cubed. So what is my set? My set contains elements of the form x cubed, that is x takes these 5 values. So and my set contains x cubed, that is minus 8 for this, minus 1, 0, 1 and 8. So this will be my set. So before such that you have the form of the element. This is the form of the element. Now, C is a set which is given in roster form 12, 18, 24, so on up to 96. So what is the set builder form for this? So to understand the set builder form, you need to find the pattern here. So what is the pattern that you observe? So as you can see, 12, 18, 24 are multiples of 6. 6 into 2, 6 into 3, 6 into 4, so on up to 6 into 16. So what is the set builder form for this? I'll make use of that property. C is a set containing elements of the form 6n, right? So all the elements are multiples of 6, so they are of the form 6n, such that n belongs to natural numbers. Yes, n takes values of natural numbers, but not all natural numbers. And what is the range of n? N is lying between 2 less than or equal to n less than or equal to 16. So n starts from 2 and goes till 16. So n is taking these values, but the elements in my set are of the form 6n. When n is equal to 2, you get 12. N is equal to 3, you get 18. N is equal to 4, you get 24. So when n is equal to 16, you get 96. So this will be one of the possible set builder form for C. Next, D is such that D is a set containing X such that X is prime and a divisor of 6. So if you take the divisors of 6, so divisors of 6 are nothing but 1, 2, 3 and 6. These are the 4 divisors for 6. But D is a set containing only those x's where x is prime also. Apart from being divisor of 6, x has to be prime also. So out of these 4, as you can see, only these 2 are primes, right? So this implies that D's set builder form will be set containing 2 and 3. So what is the number of elements in D? Again, equal to 2. So here, if you take the set B, the number of elements in set B is nothing but 5. Similarly, the number of elements in set C is nothing but the total number of elements is equal to 15. So I hope you understood the conversion from set builder form to roster and roster to set builder form. Now let us go to the second type of questions. So now, in this question, we are given that the set A is a set containing elements 1, 2, set 1, 2, 3, set 2, 3 and 5. And you are asked to fill the blanks with either belongs to or subset of. So let us look at the first one. So I want you to just remember what belongs to and subset mean. So when you use belongs to, you should have an element. So we know that every element of the set A belongs to A. And whenever you use subset, a set is a subset of A if the set contains the elements that belong to A. So if each element of a set also present in A, then that set will be a subset of A. So if you take the first blank, 1 is obviously an element of A, right? 1 is an element of A, so 1 belongs to A. 1 is not a subset of A because this is not a set. 1 is an element, so 1 is not a set, so there is no question of being a subset. So 1 belongs to A. Next, let us go to the second one. Set containing 1, 2. Is it a subset or does it belong to? So, what are the elements present in A? The elements present in A are 1, 2, set 1, 2. As you can see, set 1, 2 is also an element of A. So you have 1, 2, 3, 4, 5, 6 elements. So you have 6 elements in A. So one of the element is set 1, 2. So obviously set 1, 2 belongs to A is right. But as you can see, if you take set containing 1 and 2, the element 1, take the element 1, the element 1 is also present in A. The element 2 is also present in A. So if you take this as a set containing 2 elements 1 and 2, 1 is also present in A, 2 is also present in A. So this set is also a subset. So set 1, 2 belongs to A as well as set 1, 2 is a subset of A. So here in this blank you can have both these symbols, both are right. Let us go to the Next question, set containing 2, 3. So as you can see, set 2, 3 is an element of A, so belongs to is right. And the elements 2, 3, as you can see, also belong to A. Elements in this set also belong to this A, hence subset of is also right. So for these two sets, you can either write belongs to or subset, both are valid. So now let us go to set containing set 2, 3. Set containing set 2, 3, does this whole element belong to A? No. Set containing set 2, 3 is not there as an element of A. So belongs to cannot come here. Now if you take the set, this set is containing set 2, 3. As you can see, set 2, 3 is an element of A. So this belongs to A, hence this set is a subset of A. Next, phi dash A. So phi is nothing but empty set. You know that empty set is a subset of every set. Empty set is a subset of every set. But as you can clearly see, phi is also an element of A. So phi is also an element of A, so phi belongs to A is also right. So you can either write belongs to or subset of, both are right. Let us talk about set phi. Set containing phi. So is there a set containing phi as an element of A? No. But a set containing phi, phi is an element of set A, so phi is also contained in A, hence set containing phi is a subset of A. Set containing 1, 5. So as you can see, 1 is an element of A, phi is an element of A, so set containing 1, 5 is a subset of A. Set containing 1, 2, 3, 1 is present in A, 2 is present in A, 3 is also present in A, and set containing 1, 2, 3 is a subset of A. So as you can clearly see, you need to understand the difference between belongs to and subset. A subset is always a set, and whenever you write belongs to, you write an element belongs to A. So if you have 6 elements in A, there are only 6 belongs to relations. So 1 belongs to A, 2 belongs to A, set 1, 2 belongs to A, 3 belongs to A, set 2, 3 belongs to A, 5 belongs to A. So you have only 6 of them, but they can have a lot of different subsets. So now let us go to the next type of question. So the next type of questions are from the formula 2 power n. So if a set contains n elements, then the number of subsets is given by 2 power n. And these questions will be related to the concept of power set also, because power set is the set containing all the subsets. So in this question you are given that the number of elements in A is 2. So what is the number of elements in P of A? What is the number of elements in P of A? What is the number of elements in P of A? Let us try to analyze this. So in the question you are given that number of elements in A is equal to 2. So what is the number of subsets of A? So A contains 2 elements. So how many subsets of A are there? So by the formula it is 2 square, that is equal to 4 subsets. So you have 4 subsets to A. Now what is the number of elements in P of A? So what is P of A? Power set of A is nothing but the set containing all the subsets. And how many subsets does A have? 4. So there are 4 elements in the power set. So the number of elements in power set is nothing but the number of subsets of A. The number of elements of power set of A is nothing but 4. So now if you consider power set of A, now how many subsets does this power set of A have? Power set of A has 4 elements. So the power set of power set contains how many elements? 2 power 4 elements. That is nothing but 2 power 4 is 16. So you have to raise it to power 2 again. Now what is the number of elements of P of A? So you have once again powered this. So P of A has 16 elements. So how many subsets does this have? 2 power 16. So P of A contains 2 power 16 elements. 2 power 16 elements. So I hope you have understood this. So in the exam, what you need to remember is, so whatever the number of P's that you have to write those many 2 power 2's. And above the last two, you have to write the number of elements in A. So if you have the number of elements in A, in the next question, if you have the number of elements in A is equal to 3. So what is N of P of A? So you should not get confused by this. So this is a very simple question. The answer is, so you see, you count the number of P's that you have. You have 5 P's. So you have to write 2 power 2 power 2 power 2 power 2 power. You have to write 5 2's. And at last you have an A also. So in for the last two, the power has to be the number of elements in A. So the answer is 2 power 2 power 2 power 2 power 2 power 3. For each P you have to write a 2, and for A at the last you have to write the number of elements in A. So this is how you solve questions of this form. So let us look at another question in this type. This question is also based on the formula 2 power n. So the question says like this: difference between the number of subsets of A and B is 56. Find n of A and n of B. It's given that n of A is greater than n of B. So in this you have two sets A and B. A has more number of elements, B have less number of elements according to the given information. So let us suppose A has P elements, B has Q elements. So the difference between the number of subsets of A and B is 56. So if A has P elements, the number of subsets of A is 2 power P, right? And the number of subsets of Q is 2 power Q. So according to the given information, 2 power P minus 2 power Q has to be equal to 56. Now obviously if n of A is more than n of B, that means P is greater than Q. So you have to solve 2 power P minus 2 power Q is equal to 56. You have only one equation. You're asked to find both the numbers P and Q. So from one equation, usually you won't get two numbers. But here you have a special case where P and Q are integers. P and Q are positive integers, right? So from that condition, maybe you can solve this equation and get both the numbers P and Q. So now P is greater than Q. So let P be equal to Q plus some number K. So if P is greater than Q, both are integers. So I can write P is equal to Q plus some number K, some natural number K. So I'll put 2 power in the place of P. Let us write Q plus K minus 2 power Q is equal to 56. This implies 2 power Q times 2 power K minus 1 is equal to 56. So what is the prime factorization of 56? So as you can see, this has 2 power something, and this is an odd number. This does not have a 2 in it. So the prime factorization of 56 is, you know that this is 8 into 7. That is 2 cube into 7. So now, obviously if these two are equal, obviously you can have only one prime factorization for a single number. So if 2 cube into 7 power 1 is same as 2 power q into some odd number. So by comparison, q has to be equal to 3 and 2 power k minus 1 has to be equal to 7. This implies 2 power k is equal to 8 and k is equal to 3. So because p and q are integers, you cannot have multiple prime factorizations. So based on that theorem, you can find both the numbers q is equal to 3 and k is equal to 3. So q is equal to 3 and p is equal to q plus k, that is 3 plus 3 is equal to 6. So these are the two numbers. N of A has to be equal to 6, N of B has to be equal to 3. So this is how you can solve the problem. So now let us go to the next type of questions. So now let us look at this question. Write the subsets of the set A, which is set containing 1, 2 and 3. A very straightforward question. So how do I do this? So we can very clearly see that A contains 3 elements. So n of A is equal to 3. So this implies number of subsets of A is equal to 2 power 3, right? 2 power n. That is equal to 8. So this set has 8 subsets. And you're asked to write all the subsets of A. So let us write one after the other. Subsets of A are. So first let us start with empty set. So we know that empty set is a subset of every set. Next, we write subsets containing one element. That is set containing 1, set containing 2, set containing 3. All these are subsets of the set A. So I have only 3 subsets containing one element each. Now let us go for subsets containing 2 elements. There is set containing 1, 2, set containing 2, 3, set containing 1, 3. So in this way, if you write them systematically, you will not miss any subset. So you have 3 subsets containing 2 elements each. 1, 2, 2, 3 and 1, 3. That's it. And you have one subset containing all the elements. Null set is a subset of every set and every set is a subset of itself. So these two will always be there, and in between them you have to write the other subsets. So these, as you can count them, 1, 2, 3, 4, 5, 6, 7, 8. You have 8 subsets. So if you want proper subsets, so proper subset is a subset which is a subset of A but not equal to A. So if you exclude this, so number of proper subsets is equal to 2 power n minus 1. So out of all these subsets, you have to exclude itself. Then the remaining subsets are called proper subsets. You have 7 of them, which excludes this. You have 1, 2, 3, 4, 5, 6, 7 proper subsets. And if you are asked to find the power set of A, power set of A is nothing but a big set containing all these subsets. Set 1, set 2, set 3, set 1, 2, set 2, 3, set 3, 1, set 1, 2 and 3. So this is the power set of A. It contains 8 elements, that is 2 power n elements. So in the next type, so I'll ask you to express the given intervals in terms of closed or open intervals. So if x is in between 2 and 3, including 2 and 3, so what do I write x belongs to? I write that x belongs to closed 2, 3. So I use square brackets. That means closed 2, 3. That is all numbers in between 2 and 3 and including 2 and 3. And next, x is going from minus infinity to 2. So starting from the extreme minus infinity, x is going towards 2. So I write that x belongs to. So if you write this on a real number line, this looks something like this. So if you have 2 here, so x goes from minus infinity to 2. So all these numbers are okay. So how will I write this in terms of intervals? X belongs to open minus infinity, close to. So remember this, whenever you have infinities, you always use open interval. Because infinity is not a number to be closed. Whenever you write close, that means infinity exactly is also included. But infinity is not a number that can be included in the interval. So always, whenever you have infinities, we use open interval. Next, x is greater than 3. So x belongs to open 3 because 3 is not included. And it goes on till infinity, right? If x is greater than 3, from 3 it can go up to infinity. So I'll use open interval for infinity. And x belongs to R. X belongs to all real numbers. So I write x belongs to, what is the interval for all real numbers? Minus infinity to plus infinity. Right? Because real numbers span from minus infinity to plus infinity. And x belongs to R plus. So usually this R plus denotes close at 0 to infinity. That's what is usually done. So whenever you write R plus, that means you're talking about closed 0 to infinity. And if you don't want to include 0, we usually write it below. R minus except 0. That is x belongs to minus infinity R minus, that is negative real numbers excluding 0, minus infinity to open 0. So if you just write R plus, close 0 to infinity. If you just write R minus, minus infinity to close 0. If you write R minus excluding 0, then 0 is not included. So I hope you have understood these problems on intervals. Now let us go forward. So now let us go to our next topic, Venn diagrams. So we have seen the three topics, D, R and T. Definition, representation and terminology. We have done that. Now we have come to the next segment, fall in love. So this statement have to be read from reverse. So V comes first, then comes operations, then come laws, lastly you get formulas. So let us first see the concept of Venn diagram. So Venn diagrams are a way in which we can represent sets pictorially. So represent sets pictorially. So Venn is the name of a mathematician. Euler and Venn combinedly gave these diagrams. So what do we do in Venn diagrams? So in Venn diagrams, you have only two rules. So in Venn diagrams, universal set is represented by a rectangle. Universal set is represented by a rectangle. And individual sets in the problem are represented by circles or ovals. Circles or ovals. So you need to remember these two. Universal set is a rectangle. Individual sets are circles or ovals. And if there are common elements in two sets, they are represented by intersecting circles. And what is the opposite of this? If there are no common elements implies non-intersecting circles. No common elements implies non-intersecting circles. For example, let us take two sets. A is the set containing 1, 2, 3, 4 and 5. And let us take a set B, which is 3, 6, 8, 4, 9. Let's take these two sets. Now, let us represent these two sets using a Venn diagram. So what do I do? First, I take a universal set. So universal set, as we have seen, can be any set which contains all the sets under consideration. So in this question, we are considering only two sets. So universal set is a set which is bigger than the combined of this. It has to be a superset for this as well as this. That means all the elements present in A and B are present in this. So this is the universal set. I'll represent it by U. This is the universal set. Now, individual sets are represented by circles or ovals. So I'll represent this by circle. Okay. So that means these elements 1, 2, 3, 4, 5 are present in this circle. Now, if there are any common elements in two sets, they are represented by intersecting circles. So let us see whether there are any common elements or not. 3 and 4 are common if you see. So they are common. So I'll represent them using intersecting circles. So this is my set B. Now, I'll fill the elements of these sets in this diagram. So as you can see, Venn diagram has to be always filled inside out. So this is something which you need to remember. So in the topic of Venn diagram, you have the code word inside out, inside out, inside out. So you have to start filling the Venn diagram from inside. Then you have to go outside. So what is the most innermost part? Innermost part is the common part of A and B. So what are the elements common in A and B? 3 and 4, right? So 3 and 4 has to be filled in the common part. So this 3 and 4 belongs to this circle as well as this circle. That means they are present in set A as well as B. Next, we fill the other elements. So 1, 2, 5. 1, 2, 5 are elements which are present only in A, not in B. And what are the elements present in only B, not in A? 6, 8, 9. 6, 8, 9. And for example, if you take the universal set as set containing 1, 2, 3, so on up to 10, yes, this can be taken as a universal set because this contains all the elements of B as well as all the elements of A. It can contain more elements also. So once you have filled all the elements, 1, 2, 3, 4, 5 is filled. 6, 8, 9 are filled. And the universal set, that means this rectangle contains all these elements. So these elements are filled already. What are the elements which are left out? As you can see, 7 is left out and 10 is left out. So 7 and 10 lies outside these two sets in the universal set. The space outside is belonging to those elements of universal set which are not present in A and B. So I hope you have understood this concept of Venn diagram. So let us look at two more examples. So next, let us look at this example. A is the set 1, 2 and 3 and B is the set containing 1, 2, 3 and 4. So this is a special case. As you can see here, A is a subset of B. Because all the elements in A are also present in B. And the universal set is 1, 2, 3 and 4 and 5. So whenever A is a subset of B, how do we represent it in Venn diagrams? So if you draw the Venn diagram, so let me tell you two cases. So if I generally use the concept that we have learned, A is a circle and B is a circle and you have a universal set here, right? So how do I fill the elements? Inside out. So if this is A and this is B, so first what are the common elements in A and B? 1, 2, 3, all these come in the intersection. And there are no elements in A which are not present in B. And what comes in this interval? We have 4 here. 1, 2, 3, 4 are present in B. 1, 2, 3 are present in A. And the universal set is 1, 2, 3, 4, 5. That means 5 is present outside the interval. So we have a total of 1, 2, 3, 4, 5 elements in the universal set. So this is one way to represent. There is nothing wrong about it. But so whenever you have subsets, we have a better way to represent them. So whenever one set is a subset of another, what you do is you draw the universal set and you have the set A, and you'll draw a set B enclosing A. So this outer circle is set B, the inner circle is set A. So now what you do is you fill elements now. So in the set A you have 1, 2, 3. Obviously this set is contained within set B. That means A is a subset of B. It's very clear from this diagram that A is inside set B, that is A is a subset of B. So whenever you have one set subset of other, you draw that set completely inside the second set. And next you have an element 4 which is present in B but not in A. This 4 is outside A but inside B. And the universal set is the total rectangle. As you can see, universal set is encompassing all this. So 1, 2, 3, 4 have already been covered. So you have an extra 5 in the universal set. 5 is present in the universal set but not in B. 4 is present in B but not in A. This 1, 2, 3, 4 are present both in A and B. So what have you learned in this question? So whenever a set is a subset of another set, we draw that set completely inside the other set. You can also draw it like this, but here it's not very clear that A is a subset of B. Okay. Next, let us go to this question where you have 3 sets. Instead of 2 sets, you have 3 sets. A is 1, 2, 3, 4, B is 2, 5, 6, 8, C is 1, 2, 5, 9, and universal set is 1 to 10. So how do we draw the Venn diagram for this? First, let us draw the universal set. Next, let us draw circles corresponding to the sets. So let this be the set A. Now let this be set B. There are some intersection. So I'll draw an intersection. Let this be the set B. Now as you can see, set C might have intersection with A as well as B. So if I draw set C here, you cannot show the intersection with A. So what we usually do is we draw C like this, below this, so that each and every circle has intersection with the other circles. We draw 3 intersecting circles whenever you have 3 sets. Let this be A, let this be B, let this be the set C. So now let us fill the elements in these sets. So remember the code word, inside out. Say it loudly, inside out. So first, what is the innermost part? This is the innermost part. This is the part which belongs to A as well as B as well as C. So is there any element which is present in all the 3 sets? So as you can see, 2 is present here, 2 is present in B, 2 is also present in C. That means 2 is present in the common region of ABC. So here you write 2. That is the place for 2. That's a common place for all the sets. Next, these 3 are the next innermost things. So once you fill this, you go for these 3. So first, what are the elements present in both A and B? So if you see A and B, 2 is the common element, 1 is not there, 3 is not a common element, 4 is not a common element. So only 2 is a common element of A and B. So there are no elements here. Next, if you go for this is the common part of A and C. Already 2 has been obtained in this. There are no elements here. So already 2 has been obtained. So let us look at B and C. You have 2. You also have a 5 which is common. Sorry, this is for B and C. For B and C, apart from 2, you have a 5 common. So 2 has already been written. 5. 5 is present in B and C but not in A. Next, let us go for A and C. So if you go for A and C, 1 is there, 2 is there. So both 1 and 2 are common. So 2 has already been written. So 1 will be written here. So 1 is common to A and C but not present in B. So once you fill all the 3 spaces, next you go for the bigger spaces. So now, what are the elements present in set A? 1 and 2 has already been considered. They are inside the circle. So the remaining elements are 3 and 4. Go for B. 2 and 5 are already considered. You write 6 and 8 here. You go for C. 1, 2 and 5 have already been considered. 1, 2, 5 are inside C. What is the element left? 9. So I have filled the elements in ABC. Now we know that the outer rectangle is a universal set. So are there any elements in the universal set which are not present in ABC? 1, 2, 3, 4, 5, 6, 7 is missing, 8, 9, 10 is missing. So this 7 and 10 lies outside ABC but inside the universal set. So now once you fill this Venn diagram, you can answer certain questions very easily. So if I ask you, what are the elements present in A but not in B and C. That is, what are the elements present only in A but not in B and C. So what are the elements present only in A but not in B and C? So the answer would be 3 and 4. So 3 and 4 are the elements which are present only in A but not in others. So if I darken this is the area corresponding to the elements which are present only in A but not in others. So this is the area corresponding to the elements which are present only in C but not in others. So if I ask you to find elements only in B but not in others, you have to see the elements in this area, 6 and 8. Now what are the elements present in both A and C but not in B? Both A and C but not in B is this area. Belongs to both A and C but not in B. This area corresponds to the area, the elements present in both B and C but not in A. This region corresponds to the area. This region corresponds to the elements which are present in A and B but not in C. So there are no elements which are present in A and B but not in C. Next, this is the area which is corresponding to all the sets A, B, C. So whatever elements come here, they belong to all the sets. And what are the elements outside this? So the outside region corresponds to those elements which are neither present in A, nor present in B, nor present in C. So I hope you have understood this topic. Let's go forward. So let us look at our next topic, which is operations. So if you are given two sets, what are the different operations that you can do on them? For suppose if you are given two numbers, 2 and 3, what are the different things that you can do with these numbers? You can add them, you can subtract them, you can multiply them, you can divide them, you can raise one number to the power of other, so on. So these are called the operations. Similarly, what are the operations that you can do on sets? Assume that you have set A, which is 1, 2, 3, and you have set B, which is 2, 4, 5. So what are the operations that you can do on these sets? So there are 5 operations that you would do on sets: union, intersection, difference, symmetric difference, and complement. So what is union? So union is usually denoted by a capital U. So if you have two sets A and B, A union B is nothing but a set containing all the elements X such that X either belongs to A or X belongs to B. So if you take an element, if it either belongs to A or it belongs to B, then it belongs to A union B. So let us see what A union B is for these sets. A union B is equal to set containing. Now let us take the element 1. So element 1 belongs to A, right? So if the element belongs to A or B, then the element belongs to A union B. So 1 is belong to A union B. Let us take 2. 2 belongs to A as well as B. So it might belong to one of the set or this set or both. Or means it can belong to either one or both of them also. So 2 also belongs to A union B. 3 also belongs to A union B. 4 belongs to B. And 5 also belongs to B. And if you take 6, 6 does not come in A union B because 6 neither belongs to A nor it belongs to B. So A union B is the set of elements which are either belonging to A or to B. So we denote it by union. U denotes union. And union, for union you have to remember the word or. Union means either A or B. Okay. Next, let us go for intersection. So A intersection B is equal to set X such that X belongs to A and X belongs to B. So if an element is common to A as well as B, that means an element is belong to A as well as it belongs to B, then it belongs to A intersection B. So A intersection B is the set of elements which belong to A as well as B. That means you have to take the common elements. So if you take these two sets, the common elements are 2 and 2, right? 2 is belong to A and also to B. So A intersection B is a set containing 2. None of the other elements 1 and 3 are not present in B. 4 and 5 are not present in A. So they don't come in A intersection B. So A intersection B is a set containing both the elements present in both A and B. Next, A minus B is nothing but X such that X belongs to A and X does not belong to B. So you have to remove the elements of B from A. So if you have the set 1, 2, 3, if you have the set 1, 2, 3, what is A minus B? A minus B contains those elements which are present in A but not in B. So 1 is present in A, it is not present in B, so 1 comes here. 2 is present in A and also present in B, so 2 gets removed. And 3 is present in A and not in B, so 3 comes in A minus B. So effectively, if you want A minus B, you have to remove the common elements of A and B from A. So what is B minus A? Conversely, B minus A is the set of elements which are present in B but not in A. That means you have to remove the common elements from B. So if B is 2, 4, 5, 2 is the common element. So you remove the 2. So the remaining elements 4 and 5. So A minus B is set 1, 3. B minus A is set 4, 5. So simply remember that to get A minus B, you have to remove the common elements of A and B from A. To get B minus A, you have to remove the common elements of A and B from B. A minus B is not same as B minus A. Is it clear? A minus B is not same as B minus A. Next, A delta B is nothing but X such that X belongs to A and X does not belong to B, or X does not belong to A and X belongs to B. So that means A delta B are the set of elements which are present in A minus B or B minus A. That is, A delta B can be written as A minus B or B minus A. So you just need to union these two. That gives you A delta B, that is equal to set containing 1, 3, 4, 5. So A delta B is called the symmetric difference of A and B. So the symmetric difference of A and B is A minus B union B minus A. So why is this called symmetric difference? Because A delta B and B delta A will be same. So what is B delta A? B delta A is B minus A union A minus B is same as this. So that's why this is called symmetric difference. It doesn't really matter in which direction you do. So A delta B will be same as B delta A. This is not true for difference. A minus B is not same as B minus A. So that's why the third operation is called difference. The fourth operation is called symmetric difference. Now let us go to the fifth. A complement is given by universal set minus A. Or in English, A complement is the set of elements which are not present in A. A complement is represented by A superscript C or A superscript dash. Both represent A complement. So A complement are those elements in the universal set which does not belong to A. So the universal set is 1, 2, 3, 4, 5, 6. So what is A complement? A complement are those elements which does not belong to A. So 1, 2, 3 belong to A. So what is A complement? A complement is nothing but set of elements 4, 5, 6. What is B complement? B complement is nothing but set of those elements which does not belong to B. So B has 2, 4, 5. What are the elements which does not belong to B? 1, 3 and 6. So that will be the B complement. So mathematically, what is B complement? B complement is universal set minus B. A complement is universal set minus A. So I hope you have understood the 5 operations. Union, X belongs to A or B. Intersection, it has to belong to both common elements. Difference, set of elements which belong to A but not to B. Symmetric difference is A minus B union B minus A. Complement is the set of those elements which don't belong to a particular set. And mathematically you need to calculate universal set minus A. And universal set changes from question. Whatever you assume as universal set in the question, you have to subtract A from this to get A complement. You subtract B, you get B complement, so on. So once you have understood this, so let us understand these operations using Venn diagrams. So first let us take the operation A union B. So we have seen that A union B is nothing but set of elements X such that X belongs to A or X belongs to B. So X either belongs to A or X belongs to B, then X belongs to A union B. So if you take the Venn diagram, see universal set, set A and set B. So what is the region correspond to A union B? So what are the elements that you get in A union B? So if an element has to belong to A union B, it might be present in A or in B or in both. Hence, the region corresponding to A union B will be this. So whatever elements are present in this complete region comes under A union B. So if you take A intersection B, A intersection B is nothing but set of elements X such that X belongs to A and X belongs to B. It means if an element has to belong to A intersection B, it has to belong to A and B. That means it has to be the common region of A and B. It has to belong to the common region of A and B. So whatever elements are present in this region, those elements come under A intersection B. So with respect to intersection of two sets, you have an important term called disjoint sets. So two sets are called disjoint sets if there is no intersection between these two sets. So if A intersection B is a null set, then A and B are called disjoint sets. So if you draw the Venn diagram, so the circles correspond to set A and set B if they are not joined. So if they are joined together, that means there is some intersection. So if they are not joined, that means they are disjoint sets. Or even if I join them, if there is no element in the intersection part, then they are called disjoint sets. For example, if I say the set A is the set of all odd numbers and set B is the set of all even numbers. So is there any element which is common to both of them? Is there any number which is both even and odd? The answer is no. Hence, these two sets are disjoint sets. Similarly, if I say that A is a set containing numbers of the form 2 power n where n belongs to natural numbers. That means set A is the set of, if you write this in roster form, n is 1 first, so 2 power 1, 2 square, 2 cube, so on. So let this be set A. And set B is a set containing numbers of the form 3 power n where n belongs to natural numbers. So first let n be 1, next n be 2, n be 3, so on. So you get 3 power 1, 3 power 2, 3 power 3, so on. So do you see that these two sets don't have any intersection? There is no common element in these two. Hence these two are called disjoint sets. So next let us go for difference. A minus B. So A minus B corresponds to those elements X such that X belongs to A and X does not belong to B. So I need those elements of A which belongs to A and does not belong to B. So as you can see, this region corresponds to A and also B. So in A minus B, you won't get this region. So you get only this region. So this is the region corresponding to A minus B. So whatever elements are there in this region, you have to report them in A minus B. Similarly, what is B minus A? B minus A is nothing but set of elements X such that X belongs to B and X does not belong to A. So now the elements have to belong to B but not to A. So if this is A and this is B, so this will be the corresponding region. So X has to belong to B but not to A. So this region does not come. So effectively, as you can see, A minus B, you need to remember this. In A minus B, what you do is, you remove the elements of intersection from A. Similarly, from B, in B minus A, you remove the elements of intersection from B. And next, if you have A delta B is nothing but A minus B or B minus A. That means you can have elements either in this region or in this region. So what is the region correspond to A delta B? So this region or this region. So the elements which belong to either this region or this region belong to A delta B or symmetric difference of A and B. So out of all the different operations, this is the operation that you tend to forget. Because minus, whenever you see minus, you'll understand you need to subtract some number of elements. You can remember that. Union and intersection come so often that they'll be registered in your mind. This is the operation that you need to remember separately. So if you want, you can read it aloud. A delta B, I want you to read it aloud. A delta B is A minus B union B minus A. Read it and visualize it. So A delta B is A minus B union B minus A. Delta is in some way difference. Delta in coordinate geometry is representing a triangle. In calculus also, remember that delta represents some sort of difference. So delta A is the difference in A in calculus. So that symbol has been used here. So A delta B, delta is the difference, symmetric difference. Symmetric because A delta B will be same as B delta A. So now let us go to the last operation, which is complement. Next, A complement, A superscript C, small c, or A superscript dash is nothing but those elements, set containing those elements such that they don't belong to A. So A complement is also called not A. So what are the elements that are not present in A? Obviously, we take some universal set in any problem. So A complement is also defined as U minus A. It is universal set excluding the elements in A. So this is the region corresponding to A complement. So all the region excluding the region A. So whatever elements are present in this region come under A complement. So now that you have understood all the 5 operations, let us apply them in some problems. So let us go to our next topic, which is loss of sets. So you have a lot of laws which you need to remember in sets. So let me tell you the most important of the laws. So first, the most important law that you need to remember is De Morgan's law. It is a law which comes in different chapters, in other chapters also. So De Morgan's law says that if you have 2 sets A and B, A union B whole complement is equal to A complement intersection B complement. And A intersection B whole complement is A complement union B complement. Very simple laws. These are named laws. So this is the most important law that you need to remember in set theory. A union B whole complement is A complement intersection B complement. And A intersection B whole complement is A complement union B complement. So if you have a union here, it becomes intersection here. If you have an intersection here, it becomes union here. And the next most important law that you need to remember is distributive law. That is, if you have A union B intersection C. A union B intersection C, this can be written as A union B intersection A union C. So you can expand it like you expand brackets. For that, if you have union inside and intersection inside, you can do that. And A intersection B union C is A intersection B union A intersection C. So these are the two laws which you need to remember specially. And all the remaining laws are very straightforward. A union phi. If you add empty set to A, you get A itself. And if you take the common elements in A and phi, you get phi itself. So A union phi is equal to A intersection phi is equal to phi. It's called identity law. And A union A, if you union same sets or intersection same sets, you get the same set as the answer. And A union B is same as B union A, that is commutative law is valid for union and intersection. And A complement whole complement is equal to A. If you complement any set twice, you get the original set. And A union A complement, you get this universal set, that is elements in A and elements not present in A combinedly form universal set, obviously. And A intersection A complement is phi, because A and A complement does not have any common elements. So these are the laws that you need to remember. So the most important law is De Morgan's law. A union B whole complement, A complement intersection B complement. A intersection B whole complement is A complement union B complement. So I hope you have remembered these laws. So these are very straightforward. These laws are very straightforward, but we'll try to prove this law using Venn diagram. We'll try to prove this and this using Venn diagrams. So to prove De Morgan's law, let us plot the region correspond to A union B whole complement, and let us plot the region correspond to A complement intersection B complement. If both represent the same regions, then I can say that these two sets are equal, right? So first, let us try to shade the region corresponding to A union B whole complement. So you know what A union B is. So this is my A union B. So if this is my A union B, what is A union B whole complement? A union B whole complement is nothing but all the elements except A union B. Yes, I need to remove this. So the region remaining is what I am shading now. So the region represented by the vertical lines is the region corresponding to A union B whole complement. This A union B whole complement is represented by the region with vertical lines. Now let us go to the region A complement intersection B complement. So for that, first let us draw A complement. A complement is all the region except A. So if you remove A, so all the region except the region corresponding to A. So this is my A complement. Next, what is my B complement? B complement is nothing but all the region excluding B. So let me draw B complement using vertical lines. So what is B complement? So all the region except B. So I should not go inside B. So all the region except B. So the region corresponding to horizontal lines is A complement. The region corresponding to vertical lines is B complement. So I want A complement intersection B complement, that is the common region of these two. That is the region represented by checked portion. So the checked portion represents A complement intersection B complement. So do you clearly see that the portion represented by vertical lines here is same as the region represented by checks here? Yes. Hence, I say that these two sets are equal. So this is how you prove that two sets are equal using Venn diagram. Now let us try to prove one of the distributive laws, that is A intersection B union C and A intersection B union A intersection C. So let us see whether both of these sets represent the same area in the Venn diagram. So what does this set represent? A intersection B union C. What is A? A is this set. So I am shading A using horizontal lines. Next, I'll shade my B union C using vertical lines. B union C is all of B and C. So that is this region, right? This region is the region corresponding to B union C. So now I want the region corresponding to A intersection of B union C, that is the intersection of the horizontal lines and the vertical lines. So always remember that intersection gives you checked area. So this is nothing but the area represented by checks. That is this area, if you closely observe. So this is the region represented by this is the region which comes under A intersection B union C. So now let us go to the next section. So what is A intersection B? So A intersection B is the region common to A and B. So that is this line. So this region is the region A intersection B. Next, what is the region corresponding to A intersection C? So A intersection C is the common region of A and C. That is, let us write this as this region. So now I want the union of these two regions. So what is the union of these two regions? Union means everything encompassed. So the union of these two is nothing but the region corresponding to this boundary. So in union you get both of them. That's the region corresponding to both these areas. So do you see that this region and this region are exactly same? Yes. Hence A intersection B union C is exactly same as A union B, A intersection B union A intersection C. This region is exactly same as this region. So this is how you prove distributive law using Venn diagrams. Now let's go forward. So finally, we have reached our final topic, which is formula, for which F stands for. So this is the most important topic in set theory, and this is where most number of questions are asked. So in the formula, the first and most important formula is the number of elements in A union B is equal to n of A plus n of B minus n of A intersection B. So the number of elements in A union B is not just n of A plus n of B. This is n of A plus n of B minus n of A intersection B. So this is the most important formula. Let us see this using example. So for example, if you have the set A is 1, 2, 3 and 4, and let us say that you have set B which is 2, 4, 6 and 8. So what is A union B? A union B is nothing but the elements which are either present in A or present in B. You need to combine these two sets. So you have 1, 2, 3, 4. You have these 4 elements. And if you go to set B, you have the first element as 2. 2 has already been included. So you don't need to write it twice. You should not write it twice. And 4 has been already included. You should not write that 4. Because if you write 4 again, the elements will not be well distinguishable. So 2 and 4 should not be written. So 6 and 8. So as you can see, n of A union B is 6 is equal to, you have 6 elements in n of A union B, is not just 4 plus 4, n of A is 4 n of b is 4. If you directly add the number of elements here, so you can see that this 2 and 4 are being counted twice. So you need to subtract them once. That is, you need to subtract the 2 elements, because A intersection B is nothing but set containing 2, 4. So how many elements are there in A intersection B? There are 2 elements. So 6 is equal to 4 plus 4 minus 2. So this is how this property works. And once you understand this property, there is a special case for this property, which is n of A union B is equal to n of A plus n of B if, so when will n of A union B be equal to n of A plus n of B? Simply when n of A intersection B is 0. It means there is no element in intersection. If A intersection B is equal to 5, or A comma B are disjoint. So in the problems, when A and B are disjoint sets, you can directly say that n of A union B is n of A plus n of B. So next, the third property is n of A minus B. N of A minus B is not n of A minus n of B. N of A minus B is n of A minus n of A intersection B. We have seen this. When you want to calculate A minus B, you need to remove the common elements of A and B from A. So n of A minus n of A intersection B. And you can see this from Venn diagram also. So if you have the Venn diagram, so if you have two sets A and B, what is A minus B? A minus B is this region. So here, what are you doing? So this is nothing but the total region A minus the common part. So n of A minus B is n of A minus of n of A intersection B. Right? So you can observe this condition from this also. What is n of A minus B? A minus B is nothing but from A you have to subtract the common elements. I want those elements of A which are not present in B. 2 and 4 are present in B. So I'll remove that. I get 1 and 3. So what is n of A minus B? But 2. There are 2 elements here. So 2 is equal to n of A is 4 minus n of A intersection B is 2. So you can see that this property works. So are the first 3 properties clear? N of A union B is n of A plus n of B minus n of A intersection B. If A and B are disjoint, then directly n of A plus n of B. N of A minus B is n of A minus of n of A intersection B. So now let us go forward. So the next formula is n of A delta B is nothing but n of A plus n of B minus 2 times n of A intersection B. So n of A delta B is n of A plus n of B minus 2 times n of A intersection B. So this can be understood using the Venn diagram. What is n of A? What is A delta B? A delta B is the region corresponding to this region and this region. A delta B is the symmetric difference of sets A and B. So can I write A delta B as A union B except A intersection B? A union B except A intersection B, right? So n of A delta B is nothing but n of A union B minus n of A intersection B. So I can directly subtract the numbers here because A union B and A intersection B. So you can very clearly see that there is no overlapping regions. So from A union B, if you subtract A intersection B, you exactly get the region A delta B. And n of A union B is n of A plus n of B minus n of A intersection B minus n of A intersection B. So that gives you this formula. So n of A delta B is n of A plus n of B minus 2 times n of A delta B. So next formula. What is n of A intersection B complement? These are auxiliary formulas. Till now, these are standard formulas. These are auxiliary formulas. That means you can remember them or you might leave them. So you just need to understand why they are working. So what is n of A and B complement? So what is the region correspond to this? So what is the meaning of this? A intersection B complement is the region corresponding to A and not in B. So what is the region which is present in A but not in B? This is same as n of A minus B, right? That is same as n of A minus n of A intersection B. So whenever you're asked n of A intersection B complement, you have to understand that this set is exactly same as A minus B because both of them represent the same region. So right. So now let us go to our further formulas. So the next auxiliary formula is n of A union B can also be written as n of A minus B plus n of B minus A plus n of A intersection B. So can I do this? Yes, because so if you want n of A union B, that means you're talking about the elements present in this place, in this region, and this region. These are the three regions which needs to be considered. And the first region can be thought of as n of A minus B. And this region is nothing but n of B minus A. I'll add the elements in this region, and n of A intersection B, the middle region. If I add elements in this region, and this region, you get the total number of elements in A union B. And the next formula is n of A complement intersection B complement is nothing but n of A union B whole complement, right? N of A union B whole complement, because A complement intersection B complement is A union B whole complement from De Morgan's laws. That is equal to n of U minus n of A union B. So to understand this, you have to understand a very basic formula. N of A complement is equal to, so what are the number of elements in any set complement? Nothing but n of U minus n of A, right? Because universal set is the union of A and A complement. This formula comes from n of A union A complement is equal to n of A plus n of A complement minus n of A intersection A complement is 0. So n of A plus n of A complement is n of U, right? So n of A complement can be written as n of U minus n of A. And using this, what is n of A union B whole complement? N of U minus n of A union B. Similarly, n of A complement union B complement is nothing but n of A intersection B whole complement, that is equal to n of U minus n of A intersection B. So these are the next set of formulas. N of A union B is this, n of A complement intersection B complement, n of A complement union B complement. So now let us go to our last formula of this chapter. So and the last formula of this chapter is the formula n of A union B union C if you have more than two sets. What is n of A union B union C is equal to n of A plus n of B plus n of C minus the summation of the number of elements in each set minus n of A intersection B minus n of B intersection C minus n of C intersection A. You have to subtract the number of elements in the intersection of two sets plus n of A intersection B intersection C. So this is the formula for A union B union C. This formula has a special name. This is called inclusion exclusion principle. This is not just a formula which is applicable for three sets. So this is a general formula. So what is the formula of n of A union B? So when you write the union of two sets, you need to add the number of elements in individual sets minus n of the intersection. Now if you have three sets, you need to add the single element numbers, and double element intersections have to be subtracted, triple element subsets have to be, intersection has to be added. Similarly, if you have four sets, this is a general formula which works. You need to add the number of elements in single sets minus number of elements in double sets plus number of elements in three sets minus number of elements in four sets. So you have plus minus pattern here. So that's why this is called inclusion exclusion principle. You include these three, you exclude the intersections, then you include the next intersections. If there are more than three sets, you exclude the next intersection, so on. So what is the meaning of this formula? So let us see why this formula is working. So if you take the Venn diagram, so if you have the sets A, B, C, A, B and C, you can see that this universal set is being divided by this A, B, C into different parts. So let us name these parts. Let this part be 1, let this part be 2, 3, 4, 5, 6, 7, 8th part. These are not the elements of the Venn diagram. These are the number of parts into which the whole plane is divided, the whole place is divided. Now, what is n of A union B union C? A union B union C corresponds to all these areas. So n of A union C, B union C is nothing but LHS is the elements, number of elements present in all these regions. That is first region plus second region plus third region plus fourth region plus fifth region plus sixth region plus seventh region. So the LHS is the number of elements present in all these regions. Now let us calculate the RHS. So what is n of A? N of A is the number of elements present in these four regions 5, 3, 1, 4. So RHS is 5 plus 3 plus 1 plus 4. This is n of A. What is n of B? Number of elements present in the whole set B, that is in these four regions. The sixth region plus first region plus second region plus third region. And what is n of C? You have to add the number of elements in these four regions. That is first region plus second region plus fourth region plus seventh region. So obviously if you just add n of A, n of B and n of C, you won't get the LHS. So you're asked to subtract some spaces. So what are the things that you're subtracting? Minus of A intersection B is this areas 3 and 1. So you're asked to subtract a 3 and a 1. And I have taken a minus common. And next, B intersection C, you're asked to subtract first area again and second area. Right? And C intersection A is first area plus fourth area. So you're asked to add all this and subtract these regions. And lastly, you're asked to add A intersection B intersection C, that is the first region. So now let us see if you do all of this, are you getting the same as LHS? So can you see 1, 1, 1, 1, 1, 1. 3 ones have been cancelled out. Next, a 2 here, a 2 here has been cancelled out. A 3 here, a 3 here has been cancelled out. A 4 here, a 4 here has been cancelled out. So all the elements of the negative sign has been cancelled. So what are left out? So what are left out? You have a 1 here, you have a 2 here, you have a 3 here, you have a 4, you have a 5, you have a 6, and you have a 7. All the remaining things have been cancelled out. That means LHS is exactly same as RHS. From the next time, you need to remember this formula very carefully. N of A union B union C is N of A plus N of B plus N of C minus intersections of 2 sets plus intersection of all the 3 sets. So that concludes the theory part of the formula section. So now let us see how questions are asked from these topics. So now that we have completed the theory portion of the topic of sets, let us take a small pause and see whether we have digested what we have read. So I hope you have taken good notes of what has been taught. So you should not see these videos as you see a movie. It is not just for entertainment. So whenever you learn something, try to note it down. So that will help you reinforce your memory. So just let us take a pause and close our eyes and just remember the topics that we have learnt. So we have a prop that is available for us. So dream, talk is come, fall in love. D stands for definition. So what is the definition of set? Well-definedness, well-distinguishability. What are elements of a set? We have seen the notation belongs to. And next we have moved on to representation part. Representation, we have 2 ways in which you can represent sets. Roster form and set builder form. We have understood what each of them is. And once we understand how to represent sets, we have gone to our next topic, T, terminology. So in that we have learned a lot of terms. Empty set, singleton set, right? Finite sets, infinite sets, equal sets, equivalent sets, and subsets, proper subsets, supersets, power sets, a lot of things. And you have understood the definitions of this. And we have done some very basic problems in these topics. And the problems will be mostly based on the formula 2 power n. So the number of subsets of a set is 2 power number of elements of the set. So next we have moved on to the next set of topics, which is fall in love. And you have to read from backwards. V stands for Venn diagram, O stands for operations, L stands for laws, F stands for formula. We have understood how to draw the Venn diagrams, and we have seen what different regions in Venn diagrams represent. And next we have gone to the operations. We have seen 5 operations that we can do: union, intersection, difference, symmetric difference, and complement. And we have seen that symmetric difference is the thing which you need to commit to memory separately. All the remaining will be very easy to remember. And A delta B is A minus B union B minus A. And once you have gone to operations, we have gone to laws. So in laws, the important law is De Morgan's law. A union B whole complement is A complement intersection B complement. A intersection B whole complement is A complement union B complement. And we have also seen distributive laws. And we have seen how to prove these laws using Venn diagrams. And once we have done that, we have finally come to our formula. And in that, we have some standard formula and some auxiliary formula. So the most important of those is N of A union B is N of A plus N of B minus N of A intersection B. So in this way, you have to have a rough idea of what is happening in a chapter before going to the next chapter. And you have to develop certain props to make you remember this. Because when you see a question, if you can categorize which topic the question comes from, you can very easily solve it. You can use the formula corresponding to that topic and you can solve it. The most important thing that you need to do in maths is categorize the questions. When you see a question, you should be able to say which chapter the question is in, and which topic the question is in, and which subtopic the question is in. So if you can categorize the topics very well, for that you need to remember all the topics that you have. You have to have a rough idea, rough sketch of what the flow of the topics is. And once you have that, it will be very easy for you to solve the questions. And let us try to solve some very standard types of questions that we encounter in this chapter, and before moving to the next chapter. Let us look at our first question. So my first question is based on some theoretical concepts. So we know that n of A union B is equal to n of A plus n of B minus n of A intersection B. So this is a standard theorem that we have. Now if n of A and n of B are given to you, so what is the condition which ensures the maximum value of n of A union B? If n of A and n of B is fixed, A union B, n of A union B will be maximum if A intersection B is equal to 0. If these A and B are disjoint sets, so you are subtracting 0 from this, so then the maximum value of n of A union B will be exactly equal to n of A plus n of B. And what is the minimum value of A union B? The minimum value of A union B will happen when one set goes inside the other set. Assume that you have one set which has 4 elements, the other set which has 7 elements. If these two sets are disjoint sets, then A union B will contain 4 plus 7, that is 11 elements, because there is no intersection. And so if one set lies inside the other, it's obviously the smaller set lies inside the bigger set, then n of A intersection B will be maximum, and this ensures the minimum value of n of A union B. So n of A union B will be exactly same as the number of elements in the bigger set. So the maximum value of n of A union B will be equal to n of A plus n of B when the sets are disjoint. The minimum value of n of A union B is the maximum of these two numbers. Obviously, because the smaller set will go inside the bigger set, so A union B will be the bigger set itself. Hence, the minimum value of n of A union B is the maximum of n of A and n of B. Similarly, what is the maximum value of n of A intersection B? So when two sets are given to you, what is the maximum value of n of A intersection B? It's nothing but the minimum n, which is there, the minimum of n of A and n of B. So obviously, because if there should be maximum intersection, one set, the smaller set, has to go inside the bigger set. Because the first set has 4 elements, the second set has 7 elements, there cannot be more than 4 common elements. If all the elements of A are also present in B, then you have all the 4 common elements, then n of A intersection B will be maximum equal to 4. So I hope you understood this concept. Maximum value of n of A intersection B is minimum of n of A and n of B. So once we have these 3 formulas, these are very useful formulas. So let us take this question. N of A is given as 4, n of B is given as 7. What is the maximum and minimum value of n of A union B? So the maximum value of n of A union B is nothing but n of A plus n of B. This happens when the sets are disjoint. So you have 4 plus 7 is equal to 11. That's the maximum value of n of A union B. So what is the minimum value of n of A union B? That's nothing but the maximum of these two numbers, that is 7. So that will be the minimum number, because this set has 7 numbers, this set has 4 numbers. So when you combine them, it cannot go less than 7, because there are 7 numbers in one of the set. So n of A union B will be at least greater than B. Hence 7 is the minimum value of A union B. 11 is the maximum value. If you are also asked to find the maximum of A intersection B, maximum of n of A intersection B, that will be equal to 4. So I hope you have understood this question. So let's go to the next question. So next question is, you're given that A union B union C is equal to the universal set. That is, if you combine A, B and C, you get all the elements in the universal set. And you're asked to find A minus B union B minus C union C minus A whole complement. So you're given 4 options. You're asked to find which is right. So to solve this question, so let us make use of Venn diagrams. It's a question based on Venn diagram. So let us draw the Venn diagram correspond to this set. So you have A, you have B, you have C. So let this be A, let this be B, let this be C. Now you're asked to find A minus B union B minus C union C minus B. So what is A minus B? So this is my A minus B. The elements present in A but not in B. It's A minus B. What is B minus C? B minus C is all elements present in B but not in C. So this is B minus C. And what is C minus A? C minus A. The elements present in C but not in A. So C minus A will be something like this. C minus A will be this. And you're given that A union B union C is equal to U. That means there are no elements in this outside region. This outside region is empty. This outside region is empty. So what is A minus B union B minus C union C minus A? All the shaded portion. So you're asked to find the complement of A minus B union B minus C union C minus A. Complement means all the elements except the shaded portion. So as you can see, the remaining portion is just this area, right? This area is remaining and the area outside is remaining. But area outside is a null set because all these 3 sets combinedly form the universal set. So there is no other region which is apart from A, B and C. Hence, A minus B union B minus C union C minus A whole complement is this region. So what does this region represent? Obviously, A intersection B intersection C. So option C is the right answer. So next, let us look at this question. This question, you're given that A union B union C intersection A intersection B complement intersection C complement intersection C complement is equal to what? So let us again solve this question using Venn diagram. So let us draw a Venn diagram correspond to the situation. So let us take 3 sets A, B and C. So this is A, this is B and this is C. So you're asked to find the intersection of 3 different sets. So let us try to shade all these 3 sets and find the common checked portion. So what is A union B union C? A union B union C is the region correspond to all A, B and C. So this is your A union B union C. Next, let us go for A intersection B complement intersection C complement. What does this mean? That the elements have to belong to B and should not belong to, the elements have to belong to A and they should not belong to B and they should not belong to C. So what are the elements in A which are neither belonging to B nor belonging to C? That is this region, right? This is the region which is belonging only to A but not to B and C. So till these two, till these two sets, the intersection is this. And now the third set is C complement. The third set is C complement, is all the elements except those present in C. All the elements except those present in C. So let us shade this region using slant lines. So all the region except that region corresponding to C. If we just leave C, we just need to shade the whole region except C. Now you want the intersection of all the three sets. That is, you want the region where horizontal lines are there, vertical lines are there, as well as checked lines are there. So can you see the region? So this is the region which we are talking about. This is the region which contains all the three lines. So this will be the region that you want. So let us go to the options and see which region corresponds to this. B intersection C dash. B intersection C dash, elements in B but not in C. No. A intersection C is this region, not this region. B dash intersection C dash, elements which does not belong to B and does not belong to C. So if we just have B dash intersection C dash, this is nothing but B union C whole dash, everything except B union C. So you get the outside region also with this. So I just want this region. So answer is none of these. So in this question, you're given that A capital N is the set containing An where N belongs to natural numbers. So what is the meaning of this? So An is nothing but a set containing the elements of the form A into N where N belongs to natural numbers. So N is equal to 1, 2, 3, so on. So what is A into N? A into 1, A into 2, A into 3, A into 4, A into 5, so on. It is A, 2A, 3A, so on. That is, An denotes the multiples of A. Multiples of number A. Similarly, Bn denotes B into N where N belongs to natural numbers. So N is equal to 1 gives B, N is equal to 2 gives 2B, N is equal to 3 gives 3B, so on. So B, 2B, 3B, so on. That are multiples of B. And Cn denotes C, 2C, 3C, so on. These are nothing but multiples of C. So An denotes multiples of A, Bn denotes multiples of B, Cn denotes multiples of C. Now, you're given that A, B, C are three natural numbers and B and C are co-primes. Co-primes means that B and C do not have any common factors except one. B and C do not have any common factors except one. That's the meaning of B and C being co-primes. Right? Now, you're given that Bn intersection Cn. Bn intersection Cn. So Bn is the multiples of B, Cn is the multiples of C. So what is the intersection of these two? So we know that the intersection of these two will be the LCM of B, C, N, right? Because if you take the multiples of 2 and the multiples of 3, if you take B as 2 and C as 3, Bn denotes the multiples of 2, Cn denotes the multiples of 3. So what are the common elements present in these two? the common elements are the multiples of 6. The multiples of 6 are there in 2n as well as 3n. So if you have to intersect bn and cn, you need to take the LCM of b and c of n. Because b and c are co-primes, the LCM of b and c is nothing but bc of bc of n. And this is given as dn. This implies d has to be equal to bc. So do you understand why LCM of b and c is b into c directly? Because b and c do not have any common factors. So HCF of b comma c is equal to 1. And in 10th class you have learned that LCM of BC into HCF of BC is equal to B into C. HCF is 1, so LCM has to be equal to BC. Hence, D has to be equal to B into C. So option C is the right option. So in this question you are given that n of A is equal to 200, n of B is equal to 300. And n of A intersection B is equal to 100. You're asked to find n of A complement intersection B complement. So from these three informations, finding n of A union B is very straightforward. N of A union B is n of A plus n of B minus n of A intersection B. That is 200 plus 300 minus 100, which is equal to 400. So does this have anything to do with this question? Yes, because you know that A in complement intersection B complement is A union B whole complement. A union B whole complement. So n of A complement intersection B complement is n of A union B whole complement, that is equal to number of elements in universal set minus n of A union B. So now, sorry, you're given, so I have misinformed the question. So in this question, you're given that n of A complement intersection B complement is equal to 300. If so, n of U is equal to how much? That's the question. So if n of A complement intersection B complement has to be equal to 300, how many elements should universal set have? So if that is the question, this implies n of A union B whole complement is equal to n of U minus n of U minus n of A union B is 400 is nothing but n of A complement intersection B complement. Right? N of A complement intersection B complement is 300, which is equal to this, which is equal to this minus this. This implies n of U has to be equal to 400 plus 300 is 700. That means there should be 700 elements in the universal set. Now let us go to the next question. So this is a very typical question in the topic of Venn diagrams. So you're given that the number of elements in the universal set, that is 100 students are considered. 100 students in a class are considered. In them, the number of students who passed in English is 15, number of students who passed in maths is 12, science is 8. And the number of students who passed both in English and maths is 6, both in maths and science is 7, both in science and English is 4. And the number of students who have passed in all the three subjects is 4. If that is so, you are asked to find the number of students who passed in English and maths but not in science, and the number of students who passed in maths but not in science but not in English. That means the number of students who passed only in maths, and the number of students who passed in more than one subject. So these are the three things that are asked of you. So these three things can be very easily found by using Venn diagram. So let us draw the Venn diagram corresponding to this information. So you have a universal set which is represented by the rectangle. So you have three sets, A, B and C. A, B and C. Now, we know that the Venn diagram has to be filled from inside out. So first let us fill the number of elements, the number of students that fall in this area. So how many students have passed in both science, maths and English? So let us write this science, let us denote this by maths, let us denote this by English. So how many students are, we don't start from here, we start from here. How many students have passed in both science, maths and English? That is this region. So this region has 4 students, right? Next, so how many students have passed in science and maths? Science and maths, 7 students have passed. Already 4 students are here. So the remaining 3 students are here. So how many students passed in English and science? English and science, 4 students. So this whole intersection has 4 students. So already 4 students have come here. So there are no students here, 0. Next, how many students are passed in maths and English? There are 6 students. So this whole region contains 6 students. 4 students are already there. So the remaining 2 students are here. Now, what is the number of students who passed in science? Total 8 students. 7 students have already come, so you have 1 student here. Similarly, number on maths is 12. 9 has already been considered, so the remaining 3 are here. English, you have 15 passes. So 4 plus 2 is 6. You have 6 already taken care of here, so the remaining 9 comes here. And we know that the universal set has 100 students, but not all the 100 students have been accounted. So 9, 10, 16, 20, 22 students have been accounted. So the remaining 78 students have been unaccounted. That means the remaining 78 students are outside this set. So now you're asked to find the number of students who passed in English and maths but not in science. Who passed in English and maths but not in science. That means just English and maths. So English and maths you have 6 students total, but I don't want the students who passed in science. So you have 2 students. So this answer is 2. So the number of students who passed only in maths but not in science but not in English. So they have to pass in maths, but they should not belong to science, they should not belong to English. So the remaining students, 3 is the answer to this question. So these are the number of students who passed only in maths, not in any other subject. So the remaining of them have passed, in other subjects also. So the number of students who passed in more than one subject. So these students have passed in exactly one subject. So this guy has passed only in science but not in maths and English. These guys have passed only in maths but not in science and English. So these 3 areas represent the number of students who passed in only one subject. I want the number of students who passed in more than one subject. That means the intersection students have passed in more than one subject. So this and this region have passed in exactly 2 subjects. This region students have passed in all the 3 subjects. So number of students who passed in more than one subject will be 4 plus 3 7 plus 2 is 9. So this will be equal to 9. So these will be the answers to these questions. So in this question you are given that out of 64 students, 45 students have passed in maths, 10 students have passed in maths as well as biology. The number of students who only passed in biology is equal to what? And it's given that all the students have passed either in maths or biology. There are no students who have failed in both subjects. So let us draw the Venn diagram corresponding to this question. There are only 2 sets. So if you draw the Venn diagram, so let us take that this set corresponds to the set M. This set corresponds to the set biology. So the students present in this circle passed in maths. The students present in this circle has passed in bio. So the students who have passed both in maths and bio come in this region. Right? Now let us fill the Venn diagram. So Venn diagram is always filled inside out. The number of students who have passed both in maths and biology is 10. So there are 10 students here. The number of students passed in maths is 45. 10 has already been there. In this complete set there are 45 students. 10 has already come here. So the remaining 35 are here. Now we are asked to find the number of students who have passed only in biology. This is being asked. And according to the given question, it's given that all the students have passed either in maths or in biology. That is, n of m union b is equal to 64. So as you can very clearly see, this region plus this region plus this region corresponds to m union b. So 64 has to be equal to 35, that is m minus b, plus 10 plus x. X is number of students who are passing in only biology, right? So let us take this as x. So this implies x is equal to 64 minus 45 is equal to 19. There are 19 students who have passed only in biology. So in this question, you given that a college awarded 38 medals in football, 15 medals of basketball, 20 medals of cricket. So there are a total of 38 plus 15 plus 20. That is the total number of medals that are being distributed. And it's given that all these medals are being distributed for a total of 58 men. And only 3 of the men got medals in all 3 sports. If that is so, find the number of men who received medals in exactly 2 sports. How do we do this? So, what are the total number of medals that you have? So, total number of medals distributed is equal to 38 plus 15 plus 20, right? 38 plus 20 is 58, 68 plus 5 is 73. Total of 73 medals have been distributed. And they have been distributed among 58 men. So out of 58 men, some men would have got a single medal, some men would have got 2 medals, and some men would have got all the 3 medals. So let us say that X got medals, X got single medal. So let us say that X men got single medal, Y men got double medals, and Z men got all medals. So X men got single medal, Y men got double medals, and Z men got all medals. And according to the given question, you're given that X plus Y plus Z is equal to 58. The total number of these men is equal to 58. This is the first equation. And the second equation is only 3 men got medals in all 3 sports. Z is equal to 3. So now with this information, can you find the number of men who got medals in exactly 2 sports? So I hope yes. So if you put Z is equal to 3, you get X plus Y is equal to 55, right? If you put 3 here, if 3 goes onto that side, you get 55. And the total number of medals have to be 73. So what are the total number of medals? Total medals given as 73, but according to this assumption, the total number of medals is X plus, because they are single medalists, so you have X medals going to these men. Y got 2 medals each, so 2 Y medals have been spent, plus 3 Z medals have been spent is equal to 73. So Z has been already taken as 3. So this implies X plus 2Y is equal to 73 minus 9 is 64. Now you have one equation here, you have another equation here. So let us say that these two are equations 2 and 3. So if you subtract one from the other, you get Y is equal to 64 minus 55 is. So Y is what you're asked to find, that is the number of double medalists. So Y has to be equal to 9. So this answer is 9. How many single medalists? If you just put y is equal to 9, you get 46. So there are 46 single medalists, 9 double medalists, and 3 triple medalists.